Hello, class. In this chapter, we're going to learn about light. We see objects in one of the two ways. One, the object may be the source of the light, like a light bulb, fire, or star. The second way is more commonly we see objects by light reflected from it. Light very often travels in a straight line. We represent light using rays, which are straight lines coming from an object. This is an idealization, but it's very useful for geometric optics. This reasonable assumption is the basis of the ray model of light. Although light rays leave each point in many different directions, normally only a small bundle of these rays can enter the pupil of the observer's eye. If the person's head moves to one side, a different bundle of rays will enter the eye from each point. When light strikes the surface of an object, some of the light reflects. The rest can be absorbed by the object, like heat, or part can be transmitted through if it's like glass or water. For a very smooth, shiny object, over 95% of the light may be reflected. When a narrow beam of light strikes a flat surface, we define the angle of incident to be the angle of incident ray that makes with the normal to the surface, and the angle of reflection is the angle the reflected ray makes with the normal. The law of reflection states that the angle of reflection equals the angle of incident. When light reflects from a rough surface, the law of reflection still holds, but the angle of incident varies. This is called diffuse reflection. Because of diffuse reflection in all directions, an ordinary object can be seen at many different angles by the light reflected from it. When you move your head to the side, different reflected rays reach your eye from each point on the object as seen in Figure A. So with diffuse reflection, your eye sees reflected light at all angles. However, with specular reflection, like a mirror, your eyes must be in the correct position. For our first example, we have two flat mirrors that are perpendicular to each other. An incoming beam of a light makes an angle of 15 degrees with the first mirror. What angle will the outgoing beam make with the second mirror? Well, first, let's sketch the path of the beam as it reflects off the two mirrors, and draw the two normals to the mirrors for the two reflections. Then just use geometry and the law of reflection to find the various angles. The first step is to solve for theta 1, which we know is 15 degrees, and which we know that 15 degrees plus theta 1 equals 90 degrees. So therefore theta 1 must equal 75 degrees. Now due to the law of reflection, theta 2 must equal theta 1, which is 75 degrees. And according to the right triangles, theta 2 plus theta 3 equals 90 degrees. Well, we know theta 2 equals 75 degrees, so theta 3 must equal 15 degrees. And again, according to the law of reflection, theta 4 must equal theta 3, which is 15 degrees. And we know that theta 4 plus theta 5 equals 90 degrees, with theta 4 equaling 15 degrees, theta 5 equals 75 degrees. So the outgoing beam that makes with the second mirror is 75 degrees. Now what you see when you look into a plain flat mirror is an image, which appears to be behind the mirror. Also, you don't see yourself as others see you because left and right appear reversed in the image. The figure below shows how an image is formed by a plane mirror according to the ray modeling. We are viewing the mirror on the edge in the diagram, and the rays are shown reflecting from the front surface. Rays from two different points on the object are shown. Two rays are shown leaving from a point on the top of the bottle and two more from a point on the bottom. Rays leave each point on the object going in many directions, but only those that are enclosed in a bundle of rays that enter the eye from each of the 2 points are shown. Each set of diverging rays that reflect from the mirror and enter the eye appear to come from a single point behind the mirror. called the image point, as shown by the dashed lines. For each point on the object, there is a corresponding image point. Let's concentrate on the two rays that leave point A on the object and strike the mirror at point B and B'. Now, because the law of reflection, angles ADB and CDB are equal right triangles. Thus, the image appears as far behind the mirror as the object is in front. The image distance, DI, equals the object distance, D sub O. We also see that the height of the image is the same as that of the object. The light rays do not actually pass through the image location itself and would not appear on the paper or film at the location of the image. Therefore, it is called a virtual image. This is to distinguish it from a real image in which light does pass through the image and therefore could appear on film or electric sensor placed at the image position. Now, our eyes can see both real and virtual images, and later on we'll see that curved mirrors and lenses can form real and images as well as virtual images. For example, like a movie projector lens can produce real images that is visible on a screen. In this example, we have a woman that is 1.6 meters tall and stands in front of a vertical plane mirror. What is the minimum height of the mirror, and how high must its lower edge be from the floor if she were to be able to see her whole body? Now, assume that her eyes are 10 centimeters below the top of her head. Well, if the woman is 1.6 meters tall and her eyes are 10 centimeters below the top of her head, then the distance AE must be 1.5 meters. And according to the law of reflection, we have two equal right triangles. So the distance BD must be half of AE. So the mirror's lower edge is 0.75 meters above the floor. And the distance FB equals the value of BD plus half of 10 centimeters because of the law of reflection to get 0.8 meters. So the mirror's minimum height is 0.8 meters, or half the height of the woman. Now, does the result depend on your distance from the mirror? No, you'll get the same answer according to the law of reflection. In this example, we're going to closely examine the photograph that reveals that in the top portion, the image of the sun is seen clearly, whereas in the lower portion, the image of the sun is partially blocked by tree branches. Show the reflection is not the same as the real scene. It's a photograph right side up. If we draw a ray diagram with the photo right side up and upside down, we see that the photo is actually upside down.